On October 19th, 2025 at 11:48 p.m. Pacific Time, a chunk of the internet went dark. Snapchat, Fortnite, Ring doorbells, McDonald's mobile ordering, even the UK's tax authority website. Down Detector logged over 6.5 million reports, spanning more than 1,000 services globally. The cause wasn't a hack. It wasn't a hardware failure. According to AWS's own post-incident report, the root cause was a race condition, specifically a TOCTOU race condition in the automated DNS system behind DynamoDB. A bug pattern you can reproduce in about 20 lines of code is what took down a meaningful fraction of the internet for 15 hours. That's what this video is about. TOCTOU stands for time of check to time of use. The pattern is simple. Your code checks something is true, then later acts as if it's still true. The bug is in the gap between those two moments. Two things to get straight before we touch any code. First, this isn't just a file system thing. Yes, the classic textbook example is Unix file permissions, but the same pattern shows up in web APIs, in payment systems, in distributed databases. Anywhere you separate check from act instead of doing them as one atomic step. Second, this isn't a hypothetical edge case bug. We're going to look at 3 examples today. A classic C example you can run on your own machine right now, a web application example that's shown up in real bug bounty reports, and the AWS outage that opened this video. Same root pattern, 3 completely different scales of consequence. Let's start where TOCTOU was first studied seriously, Unix file operations. I'm going to write a small, deliberately vulnerable program, then break it. This program does 2 things. First, access, checks. Can the current user actually write to this file? Then, separately, it opens the file and writes to it. That looks completely reasonable. It's the kind of code a careful developer writes specifically because they're being careful, checking permissions before acting. The problem is that access and open are 2 separate system calls. The kernel doesn't treat them as one operation. Between them, there's a window. And I've added a 1-second sleep here, just to make that window big enough to see on camera. In the real world, that window could be microseconds, and attackers have tooling that hits it anyway. Runs fine. Now, here's the attack. While that program is in its 1-second gap, I'm going to swap the file out from under it using a Symlink, pointing it somewhere. It should never be allowed to write. In a real privilege escalation scenario, this is the move that's historically been used to redirect a privileged program's write target towards something like /etc/parserwd. I'm using a harmless decoy file here. Obviously, don't point this at real system files. The point is, the check happened against one file. The write happened against a completely different file because the path got redirected in the gap between them. Here's the fix. And the principle behind it matters more than the specific code. Collapse check and use into a single atomic operation. Excel makes the open fail if the file already exists. No separate check needed. The kernel does the check and create as one atomic step. ONoFollow refuses to follow a Symlink at that path at all. There's no gap for an attacker to land in because there's no second system call to race against. That second failure isn't a bug, it's the fix working. It's refusing to silently overwrite, which is exactly the ambiguity that caused the problem in the first place. Most of you aren't writing set UIDC binaries day to day, so let's move to where this pattern actually bites experienced developers in practice. HTTP API. Classic example from real-world bug bounty write-ups, an e-commerce coupon code. The server checks, has this code been used? Then, separately, it applies the discount and marks the code as used. Same shape as the file system bug. Check, then act, with a gap in between. Both came back successful. Both got the discount. The already used check never had a chance to catch the second request because the second request did its check before the first request finished its write. I confirmed this myself before recording. Both requests really do return success. This isn't a hypothetical. 2 layers of fix here, because at scale a single in-process lock isn't enough on its own. This closes the gap for a single process. But I want to flag something honestly. This only works if you've got one process holding that lock. The moment you scale to multiple workers or multiple servers, which is the normal case in production, an in-memory Python lock doesn't coordinate across them at all. The real fix at that scale pushes the check and set down into the database as one atomic statement. Check how many rows that statement affected. If it's 1, you won the race. You're the one who gets to apply the discount. If it's 0, someone else already claimed it a moment earlier, and you reject the request. The check and the write happen as a single atomic database operation, so there's no window for two requests to both pass the check before either one writes. This is the general pattern. Whenever you can, push check then act down into something the underlying system already does atomically, instead of doing it yourself across two separate calls. Same pattern. Now, let's see what it looks like when it happens inside one of the most heavily engineered systems on Earth. DynamoDB's DNS system has two components: a DNS planner, which watches load balancer health and produces new DNS plans, and DNS enactors, multiple of them, running redundantly across different availability zones, whose job is to take a plan and apply it to route 53. Here's what happened, in order. One DNS enactor, call it enactor A, started applying an older plan, but it hit unusual delays and needed retrees on several endpoints. While enactor A was still slowly working through that old plan, the planner kept producing newer plans. A second enactor, enactor B, picked up one of those newer plans and applied it quickly, across all endpoints. Once enactor B finished, it kicked off a routine cleanup, deleting old, superseded plans. That's normal housekeeping. At that exact moment, enactor A finally finished applying its much older plan. It overwrote the newer plan that enactor B had just installed. Critically, enactor A's earlier check, the one that should have caught, "Wait, is my plan stale?" That check had happened before the delay. By the time it actually wrote, the check was already out of date. Classic TOCTOU. Then the cleanup process saw this very old plan sitting there, identified it as outdated, and deleted it. Which sounds correct in isolation, except it had just become the only plan, because it had just overwritten the current one. Deleting it didn't roll back to the previous plan. It deleted the only DNS data DynamoDB's regional endpoint had left. The result? An empty DNS record for DynamoDB US east in AWS. Not wrong data, but no data. Every system trying to resolve that hostname got nothing back. No IP address to even attempt a connection to. And then it cascaded. EC2's internal lease management system, the Droplet Workflow Manager, depends on DynamoDB to track server state. When DynamoDB became unreachable, that system started failing too, which meant EC2 couldn't launch new instances properly, which meant the outage outlived the original DNS problem by hours. DynamoDB itself was restored in about 3 hours. Full recovery across all affected AWS services took roughly 15.